Today's lecture is Cosmological Perturbations. Again, it's going to be a very brief discussion. It's a big subject. We just want to touch on some very basic facts. Cosmic perturbations. So what is the motivation? The motivation is that obviously we do not live on exact FRW cosmology. The universe we live in is not exactly homogeneous and isotropic. What we know is that at larger scales, it is approximately homogeneous and isotropic, but there are perturbations, there are fluctuations. And the goal of cosmological perturbation theory is to understand the evolution of the perturbations on this FRW background. We want to understand this to explain why the features of the universe that we see at a smaller scale, which can be very inhomogeneous. There are galaxies and the structures, and we would like to understand by analyzing this, and also, for instance, if we look at CMB, the CMB photons that we talked about yesterday, we see that the temperature is not exactly the same on different sides of the sky. They are CMB anisotropies. If we look in one direction, some other direction, we see that there are fluctuations which are small. So we can measure those, and we would like to understand, use those measurements, those observations to understand what was the, learn something about the initial condition of our universe. And also learn about the physics that led to the evolution of that initial condition in the way that we see them today. So it teaches us about many things about the initial condition and the physics that governs the dynamics from those initial conditions until when we observed. So in order to study that, of course, we should understand how the perturbations evolve on a FRW background. Or at least this is the first step. Of course, some of the things that we see are not perturbative; they are nonlinear, and then perturbative methods might not be applicable. But they give us a very good idea of what is the general picture. Okay, so now here I'm going to discuss a very simple model first, of a simple model of a scalar field on a FRW background. And then from there, we learn some lessons and then describe what happens in a more realistic situation. So we have a scalar field on FRW. So what does it mean? We have an action for, and this is a massless scalar field, equal to 0. So we have the action, which is given by -1/2 integral. So this is the general action for a scalar field. But on FRW, if we use the FRW metric, then this action, so on FRW, this action becomes d tau d3x a to the fourth from the determinant of the metric, and then I will have 1/a² from the inverse metric. Then there is d tau of phi squared minus grad phi squared. Okay, now from here, we can derive the equations of motion. So the equation of motion for phi will be phi double prime plus twice a prime over a times phi prime minus Laplacian of phi is equal to 0. Where prime means d by d tau. And I remind you that tau is the conformal time. So the metric will look like a squared minus d tau squared plus dx squared. Oh, and we are considering flat FRW. For simplicity, and because it is relative, it is very realistic for our universe. But if it was not flat FRW, there would be complications, but analogous things could be done using, for instance, the spherical harmonics or the harmonics on hyperbola, if it was closed or it was open FRW. Okay, so we have this equation of motion, linear equation of motion for the phi field. So now phi field is not homogeneous. We want to consider perturbations or fluctuations which are inhomogeneous. Now, one property that this equation has is that it is independent of x, right? There is no explicit x dependent in this equation, which is the consequence of the fact that the background is homogeneous. That means that we can go to the momentum basis. So we can write phi of tau and x. So this phi here was phi of tau and x. We can write it or decompose it in terms of the momentum modes. And because there is no explicit x dependence, and because this equation is a linear equation, different momentum modes decoupled from each other. And also the k remains conserved. So this k that appears here is called it's called the co-moving momentum, and it is conserved. It doesn't change. For a given component of phi k, it always has the same x dependent. You can think of it as being the this k being the lower component of the momentum vector for geodesics, or is similar to that. So since we have k dot x, this k should be thought of as a lower component of momentum, which was a conserved quantity on FRW back. Okay, so now how does the equation? This is for later. How does the equation of motion look like in this momentum basis? It becomes phi k double prime plus 2 curly h phi prime plus k squared phi, these are phi k, equals 0. Where now I defined this curly h to be a prime over a, which is equal to a dot, which is equal to a times usual h that we have. And this is called the co-moving. So for reasons that it will become clear, this 1 over h is called the co-moving horizon. Okay, so now we have this equation for any k mode, and we want to analyze this. Now, one thing, so this is of course similar to the wave equation that we have on Minkowski. It's similar, except that there's this extra term, right? If this wasn't there, then it would be the same as the usual wave equation that we would get on Minkowski space. But this term introduces a scale in the problem. So there are two regimes for this equation. Well, there are two interesting regimes of this equation, which are the following. So regime 1 is when k is much bigger than this curly h, much bigger than a prime over. Then we can then the equation is approximately the same as in Minkowski. So this term will be a small correction. Since this is a small correction, and the original equation of Minkowski would have solutions which are oscillating solutions, e to the ik tau and e to the minus ik tau. In this regime, the general solution can be written as phi k of tau equals some a plus of tau times e to the I k tau plus a minus of tau e to the minus I k tau, where these a's have the property that a prime over a. So a's and a minus and a plus would be constant if h was 0. If this term wasn't there, then this would be just constants, and we would get the usual plane wave equation, or the usual oscillating exponential oscillating solution. So a prime is non-zero because there is h in here. So the expectation is that a prime over a is of order of the curly h, and therefore much less than k. And we can, using these ansatz, we can determine this a plus and a minus. So we just plug these ansatz in the equation. The leading terms would cancel. So the leading term would be this, and two derivatives acting on the exponent. The subleading term would be 2i k a prime over a plus 2i k h acting on phi k of tau equals 0. which tells us A prime over A is equal to minus H, which means that A is proportional to 1 over A. So we learned that our solution phi k of tau is approximate, so there will be even additional, even more subleading corrections. But in this regime, the solution is approximately some constant C plus e to 1 over A times the constant C plus e to the I k tau plus another constant C minus e to the minus I k. Okay, so this is the regime 1 when we have oscillating solutions. Oscillating solution whose amplitude is now changing, is changing slowly with time. This should perhaps reminds you a little bit of the WKB solutions that we have in quantum mechanics in the allowed regime, in the allowed region. Which is valid when the momentum is large, or the phase of the wave function is varying quickly. So here is that situation. The phase is varying quickly compared to the time dependence of the background. The other regime is the opposite, of course, when k is much less than h. And in this case, we can ignore the last term in this equation. So we get to leading order, we have these two terms. So one of the solutions is that phi is a constant, approximately. And then there will be the other solution. So what do we have? We have phi k double prime plus 2h phi prime is approximately 0, which gives us the two solutions, constant, and the other one would be integral d tau over a squared. So the full phi solution would be C1 plus C2 integral d tau over a squared. Again, this is approximate. It's an approximation in the limit that k times k is much smaller than h. So here, to get this answer, I just assume that phi prime is non-zero and integrated this equation twice. So integrating once gives me phi prime is proportional to 1 over a squared, and then I integrate it again to get this d tau over a squared for phi. Now, one of these solutions, so this solution is decaying. Or if we go back in time, it will be singular at tau equal to 0. Let's imagine we have some matter domination or radiation dominated universe, which is a good approximation as we go to. Radiation domination is becomes a better and better approximation to our universe as we go to earlier times. So this is the decaying one. The other one, just to contrast it with the second one, it is called the growing solution, although here it is just a constant. So I put it in quotation mark. But sometimes it is called the growing solution. Okay, so any questions so far? We just consider the scalar field perturbations of a scalar field on a Fardabaly background and identify two different regimes. The regime in which we have waves with oscillating phase, and the regime in which we have solutions which are it's superposition of a constant plus a decaying piece, no oscillation. And we have these two regimes because we are studying the equations on a background geometry which has some time dependence. So it introduces a scale in the problem. Okay, so it seems that there is no question. Now, of course, we said that K is constant. So we consider some particular phi K. K is just a label of that. These are, by the way, these are called modes. These different components phi K are called different modes of phi. So we consider a particular mode, and then there are these two regimes. Of course, the interesting question now is which regime comes first and which comes second? Or in other words, as time passes, what happens to the scale H, or what happens to the co-moving horizon? Do we go from regime 2 to regime 1 as time passes, or we go from regime 1 to regime 2, or do we oscillate between these two regimes? So this is the question that we want to understand next. So we want to ask about maybe we go to a different page. Evolution of the co-moving horizon or the curly edge. Okay, so let us assume that we have a single component cosmology, or we are dominated by single component. So we have a single component FRW. So there is a single parameter W, which let me just remind you, W is the relation between the pressure and the density. So this is a simple linear relation between pressure and density, which is a very good model for different constituents of the Fardabaly cosmology that we are dealing with. Okay, so we have a single W. We know that from the energy conservation equation, rho is proportional to 1 over A times 3, 1 over A to power 3 times 1 plus W. Right, so for instance, W is 0 for matter, and rho goes as 1 over A cubed. W is 1/3 for radiation, and rho goes as 1 over A to the 4th, and so on. for cosmological constant, W is -1 and rho is a constant, as it should. Okay, so rho goes as 1 over a cubed, and we know that h squared is 8 pi g third times rho, since we are in flat for W. So h is just h naught divided by a to power 3 over 2, 1 plus W. So therefore, the Curly H co-moving hub or conformal hub. Yeah, I'm not sure what this is called. Which is A times H is equal to H naught A to power -1 over 2 times 1 plus 3W. Okay, so what do we learn from this? What we learn is that if W is larger than -1/3, then H decays in time. As the universe expands, this co-moving Hubble decreases. Which means that the co-moving horizon increases, expands. On the other hand, if W is less than -1/3, then H prime will be larger than. So now, for most of our cosmological history, or in the Big Bang picture, we are in this ratio. So as we go back in time, we are radiation dominated, and then at redshift of about 3000, we become matter dominated. Only very, very recently, the cosmological constant becomes relevant. So for most of the evolution, we are in this regime when W is larger than -1/3, right? For radiation, W is 1/3 positive, and for matter, it is 0. So in both cases, we will be in this situation. So what happens if we are in this situation? So let me plot this. So here I want to put a co-moving scale. Or log of the co-moving. And here the log of the scale factor, which is like a time parameter. So the scale factor is growing with time. So as I go to larger scale factors, I'm going to later times. Okay, so how does the co-moving horizon look like in this plot? It looks like this, right? Remember, this is logarithmic plot, so the things are negative. Doesn't mean negative on this plot means just less than some fixed value. It doesn't mean negative h. So this is a log of 1 over h. I'm plotting distances, not the moment. And then if I consider fixed k, so a fixed co-moving momentum, then again, let us plot 1 over k on this plot, so a distance scale. So that would be the co-moving wavelengths, for instance. So the plot 1 over k, that is of course just a constant. So this is like a wavelength, so, co-moving wavelengths. So now what we see is that there are two. So these are we can identify these two regimes, right? Here we have the regime in which so 1 over k is larger than 1/h. This means that k is smaller than h. So here we are in the regime when k is less than h, and here k is larger than h. Here when k is larger than h, we have oscillations or we have waves. Here we have a constant. Also decaying, but if we say the initial condition is non-singular, then the decaying will decay fast, and essentially we are left with a constant. This regime, when k is less than curly h, or the wavelength is larger than what we call the comoving horizon, is called the super horizon regime. This regime, when the wavelength is shorter than the comoving horizon, is called subhorizon. So this is just the name. But importantly, in the subhorizon regime, we have oscillations and waves. In the superhorizon regime, we have solutions which are constant. So sometimes they are called frozen. Now, why does it happen? Why do we have these two regimes? It is not too hard to see why it happens if we go to the conformal diagram for FRW. So let us look at the conformal diagram. So we have x and we have tau. Now in conformal diagram, what we see, or what anything see, is limited to the past light cone, which on the conformal diagram is drawn in 45 degrees. So now let us consider some fluctuations here. Now we can ask if someone is sitting here, some observer, at different times, it looks what that observer sees. And of course, if we are in the radiation or matter dominated universe, there will be Big Bang singularity at tau equal to 0. So there won't be anything past. There won't be anything past this line. This should be the singularity. So what do we see? As time passes, this is the region that is being observed. So now this thing that is being observed, it could be the field itself. So you can ask, what does the field at phi at x equal to 0, how much of the other values of the field are causally connected to this point, tau and x equal to 0. So the region that is causally connected to this point, if the wavelength is very large, then at the beginning we only see a homogeneous universe with some fixed value of phi, because the wavelength is much larger than the size of the region that we are observing. So we see just a homogeneous configuration for this phi field. Now, if this field does not have a mass, or is light enough, then that homogeneous configuration would be just a solution of the equation. So that's the meaning of this frozen or constant solution. On the other hand, as we go to later times, eventually we see the gradients. We see that it's not homogeneous. Once the gradients are seen, then the field starts oscillating. And then we enter the regime of the wave regime. So we go to later time. At some point, we get to the regime when K becomes over the H. And then we go even further and we get to the regime when we have oscillations. Because now we see the gradients of the fields. So this is what you see in this diagram. With time, originally the solution is constant because the modes are super horizon and they are approximately can be thought. So the different regions in this diagram can be thought of as separate FRW universes that evolve independently. While as we go to later times, then these gradients become important, and then we will get wave solution. So this is the general. This is the intuitive reason for this change of the regime. Okay, so now if we consider, is there any question about this? So here I should emphasize that this plot was drawn under the assumption that W is larger than -1/3. So that 1/h is growing with time. Okay, so is there a question? All right. So now in our universe, again, we have perturbations. And now we see from this diagram that any perturbation that we consider as we go back in time, it will, and earlier, if we go to earlier and earlier times, eventually it becomes super horizon in the, at least in the Big Bang picture, when we have radiation dominance at early times, until we get to the Big Bang singularity. So then the question one can ask, or one should ask, what determines the initial condition for these fluctuations? So we know that initially modes are super horizon in, say, radiation dominated universe. And the question is that what is the initial condition? Or what kind of initial perturbations we have in our universe? Okay, so now I'm going to describe a particular kind of initial condition that seems to be a very accurate description of what we see in CMB, for instance, which is called adiabatic initial condition. Or adiabatic perturbations. Okay, so the idea is that let us consider a radiation-dominated universe, which is in thermal equilibrium. So we have a state of thermal equilibrium. And let us further assume that the chemical potentials are all negligible. So mu I are all 0 or approximately 0. Or in other words, there is no net conserved charge in this universe. Okay, so now we know that in this, if now here this system has some temperature, right? And temperature has a function is a function of the scale factor. For instance, if the number of relativistic degrees of freedom is constant, T just goes as 1/A. If it is changing, then T will go as, in general, T will go as 1/the number of relativistic degrees of freedom to the 1/3 A, 1/this. So if I want to plot it, log of T, then it has a behavior which looks something like this. So these straight lines correspond to 1/A behavior. So slope of -1, and then when the number of relativistic degrees of freedom goes down, then T deviates from that for while the G star is changed. So now in this diagram, you can see that so the scale factor is again, it acts like a time parameter in an expanding universe. But there is a monotonic relation between temperature and the scale factor. So temperature itself is also an effective time parameter in this cosmology. And it's the only parameter in thermal equilibrium if I set chemical potentials to 0. So if you tell me what is the temperature, I effectively know where in this history I am living. Now consider the following. So this is, now I'm going to describe the adiabatic perturbations, how they are defined. So again, we go to this conformal diagram. And we consider, so we said every mode, as we go to sufficiently early time, it becomes super horizon. So let's consider super horizon fluctuation, or let's consider a fluctuation and go to the time early enough so that it is super horizon. So we go to a time slice which is early enough when this is super horizon. This particular scale is super horizon, and then we define the perturbations by saying that we have just the temperature that is the slowly varying with that wavelength over our time slice. So here we have T1, here we have T2, different temperatures. So the temperature is changing, but with the very long wavelength, some super horizon wavelength. Then these two different points in this plot that we can go to this diagram, and these different temperatures, these different points correspond to just two different points on this plot, obviously. So this is, for instance, T1, and this is T2. So now what we see is that these 2 points are just different points along the same history. So if we were to go back in time in this point, we would experience the same history as the one that was experienced by this. Or at some, if we were to go back in time, we would eventually reach the temperature T1. So this means that this kind of perturbations that I define is by just saying that I have thermal equilibrium, and at different points I just have different temperatures. This corresponds to just having different histories at different points. At this, while I'm talking about super horizon fluctuations. Of course, when these fluctuations enter the horizon, then what happens is that then they start oscillating, and we will have acoustic waves in this radiation fluid. So the adiabatic fluctuations are just so when K is much less than H, they correspond to X1 and X2 experience the same, let's say, thermal history. So in other words, they are just indistinguishable cosmologies. The observer at point X1 and observer at point X2, they think that they are just in the same cosmology, in this experience thermal history. There's only a time shift between them. And importantly, this time shift is not something that they can measure locally. So they have no idea that there is this time shift. Only a global observer knows that if I draw this slice, then there will be a time shift between the two. But for them, it's just the same cosmology going on. Okay, afterwards, when K is larger than H, then we will have acoustic waves or sound waves in radiation fluid. Again, in a fluid, we only have one kind of wave. So just compression modes of the waves or sound waves. So there is a single degree of freedom that specifies perturbations, and this is related to the fact that we just had the temperature. to specify origin. So we had 1 degree of freedom, 1 scalar field to specify this adiabatic, to define this super horizon perturbations. As they enter the horizon, that 1 degree of freedom or that 1 field translates into the sound wave in this radiation fluid. Any question about this? Okay, how do we describe these sound waves? Well, if we go well inside the horizon, or if we go to K's, that's equivalent to saying that if we go to values of K, which are much, much bigger than this curly H, then we are effectively dealing with the equation in Minkowski. We are very close to working with the wave equations or with the equations of motion in flat space, and because we are looking at distances much shorter than the cosmological scale. So this is, for instance, is equivalent to saying that when we do experiments in our laboratories, we don't take into account the fact that we are living in some expanding cosmology. For studying the waves in the sea, in Adriatic, we don't need to care about the expansion of the universe. So this is a similar statement. And the case, the wavelength is much, much shorter than the size of the horizon size, or the cosmological scale that we have in the problem, then we can basically ignore. In that regime, we get just from the usual fluid equations, which are the Euler and continuity equation, we get a wave equation for linear fluctuations, which is very similar to the equation for the scalar field that we had, except that there is a where did it's very similar to the equation that we studied for a massless scalar field, except that it has a different coefficient in front of the Laplacian gradient. So in radiation fluid, for instance, we can work with the fluctuations of the density. So we define delta equals delta rho over rho. And then for this quantity, we can derive a wave equation, which looks like delta double prime plus CS squared K squared delta approximately equal to 0. Approximate because I have ignored, at this point, I have ignored the expansion of the universe. And of course, this is a particular momentum. So if I set CS to 1, this looks like the equation for a massless scalar field that I had before. But in radiation dominated universe, this CS squared is, or in a radiation fluid, this CS squared is 1/3. And then, of course, the solutions to this equation would be waves, right? So for instance, it will be delta of K would be something like cosine, some constant A times cosine of CS K tau. If we assume that tau equal to 0, it has 0 derivative. Now, if we need to do a more more careful treatment of this when we are in cosmology, because now we are talking about the modes that are originally super horizon. Their wavelength is very large compared to the cosmological scales, and only later this approximation becomes valid. So we want to follow this initial condition that we impose. From the time when the cosmological scale is important, the expansion of the universe is important, until the time when we go to this wave regime. And of course, to do that, one has to do a more careful job. The fluctuations of the metric are also important. So one needs to solve the relativistic version of this system. So one should consider G mu nu to be the for W metric. So G bar mu nu, which is a for W, plus some fluctuations. And then similarly, we have fluctuations of the density and pressure. And then what we do is that we consider the linearized Einstein equation. So G mu nu equals 8 pi G mu, and the linearized conservation equation. So again, this linearized. So one can solve this system. Again, there is only one degree of freedom. So there are many variables, but there are also a lot of constraints. So eventually one can reduce this whole thing to differential equation for a single degree of freedom, which at late times would agree with what we have here, but at early times will disagree with that. And if we do that, then we get a solution for this system that will look like, so I have plotted it here. So let's look at just this plot. So I just fixed some initial, some arbitrary value for the initial, for the amplitude of the waves. And then this blue curve is what one obtains by this linearization. Let's see if I can move this. Okay, no, they don't want to move. Oh. Okay. So here, just this plot is just to show you that. So I have this blue curve and the orange curve. This is just to show you that if I do this linearization in radiation fluid, so assume CS squared exactly equals to 1/3, and do this linearization and solve for this system, I'll find this blue curve. This orange curve is just a solution for this wave equation. So as you see, at late times they agree. Of course, I fixed the amplitude and the phase so that they agree, but the important thing is that this is the real solution, or the more accurate solution will have the same late time behavior as what you would expect from just waves in a radiation fluid, ignoring gravity. So the late time behavior, which corresponds to wavelengths much shorter than on the horizon, they exactly agree, and then at early times they disagree. And the scale in this plot, this is exactly the time scale. So here I can put, so this is tau, and this is delta of some particular k. And then the point between the zeros, so this is scale in this plot is 2 pi over k. So this is 2 pi over k. So the momentum is determining the scale of oscillations of the solution. Okay, so now you could ask, imagine now I squared, so imagine a little bit more realistic situation. These perturbations that we have in our universe, they are not all identical. They don't have identical amplitudes. They are, or at least they look like random fluctuations with some Gaussian spectrum. So what we do actually is that we square them and average over them, over different orientations and different wavelengths. So we can take this solution and then square it. So here I have just squared the answer and plotted that square thing in logarithmic scale. So this is delta squared k and tau. But another thing that we can do is that instead of looking at the time evolution of this, we can ask the following question. Imagine we have different modes. They all start with this adiabatic initial condition. And the important thing about that is that it fixes this initial behavior. The amplitude is a random variable, but the phase at which these fluctuations start is completely fixed when I say I have adiabatic initial condition. Because we have this constant mode at the initial, as the initial condition. A single degree of freedom that goes to a constant, so has zero derivative at tau equal to 0. Now we can now imagine, consider various values of k. So what does it do? It basically gives the same plot if I look at various values of k, except that this distance scale will be rescaled. So I will get identical solutions except up to a rescaling of this plot. So for instance, if I try to draw something on top of this, if I consider much lower k, then it should look like, okay, let me try to do something. So it can look like this. So that would correspond to, say, if this is k, if this is k1, then this corresponds to k2 less than k1. The scale of variations would be different, but it would just have a similar behavior. Now, one thing that we can do, and we actually do in real life, is that we, at some particular time, tau star, we look at all of the modes. Now, since all of them have the same history up to this rescaling, looking at all of them at a given time is equivalent to looking at one of them at different times. So if I consider some time tau star, and this tau star is supposed to be the time of the last scattering surface, from which the photons propagated to us freely. So at that time, we are looking at all of the fluctuations, whatever amplitude they have, they are recorded in this CMB fluctuation, CMB photons that we are seeing. And then we can look at it as a function of not time, but K. And then what we see is that the low K modes, they are basically showing us the early parts of this curve, while the high K modes are showing us the later part of this curve. Different cases will just be rescaled at this value tau star. So if I were to look at delta K of tau star, we would the square because the amplitudes are actually average. The amplitudes are random, Gaussian random variables. Then we would basically get the square of this diagram. Now, this is something that if you have seen the Planck map for CMB power spectrum, this might look a little bit familiar or similar to it. With a bit of imagination, you can think that, or you can make some connection between them. So this is the real map. And so again, this one let's see, this one is not in logarithmic, so this is in linear scale. But there are some more important differences. But there is some similarity, but some important differences. Yeah, I should have said that here. I took a log. So that's why this is a logarithm. So what is the reason for the difference between these curves? One is that, so let us list the reasons. One is that we are not exactly in radiation domination, like the CMB, the last scattering surface or the decoupling happened, in fact, during matter domination. So there is non-zero omega matter. There's non-zero matter. Another point is that this matter is not just made of baryons. So we saw that in the previous lecture, we saw that baryons are coupled to electrons, which are then coupled to photons. So the baryon and photon fluid is, baryons and photons, they constitute a single fluid in which we can consider waves, while there is another component of matter which we call dark matter, which is decoupled from this fluid. So the waves in the radiation fluid or in the baryon photon fluid that we have, those waves, they only communicate with the dark matter through gravitational interaction, but no pressure or no electromagnetic interaction between. So this is the second reason. So we know that, for instance, omega baryon is about 0.05, while omega matter is about omega matter is about 0.3. What is the third reason? The third reason is that in this top plot, we are looking at delta rho over rho, but in the bottom plot, we are looking at delta T over T, temperature fluctuation. So these two are not exactly the same. And then the fourth reason is that there is damping. She's got silk damp. So these waves will get damped or dissipated as they propagate. It's not an ideal fluid, and that's why the amplitude of these waves goes down. The amplitude goes down. Now, for instance, one could, now of course, one can analyze this system analytically and compute. So this line that you see here is the result of an analytic computation, and the dots are the result of observation, which, as you see, they have very good agreement. And this error bars come from the cosmic variance, the fact that we don't have many modes at very large scale. So as you see, there is a very good agreement between these plots, and this agreement comes from a very delicate choice of these various cosmological parameters. So, for instance, this knowledge of omega B and omega matter that we have, they come from fitting these curves. So if we were to change, for instance, omega B, omega baryon from what it is, keeping omega matter fixed, then that would change the relative height of different peaks in this plot. Of course, there are some combination of cosmological parameters to which the CMB power spectrum is not. Power spectrum is this average that I'm talking about. The power spectrum is not very sensitive, and other cosmological probes are being used for fixing, for breaking those degeneracies. But this is one of our main tools to determine the cosmological parameters of our universe. Okay, any question about this? Of course, there are other reasons. These are just some of the reasons. Okay, if there is no other question, then I can also say a few words about Jeans instability that leads to the formation of structures and galaxies in our universe. So since we are talking about fluctuations, it would be nice to also have an idea of how they lead to the formation of the structures and galaxies that we see. This is also a very simple idea. I just illustrate the idea and then we can go. Jeans instability. Yeah. Stability. So let us consider, so here I'm just doing an estimate for now to understand if we have a gas or a fluid with some pressure and density, and if there is gravity, what happens if I make the size of this object bigger and bigger? And the idea of Jeans instability is that if you have some matter distribution or some object with some density and pressure, and you make it bigger and bigger, eventually at shorter distances, at the smaller sizes, the gravity is totally unimportant. So for instance, when I have this cup, gravity plays almost no role in the structure of this cup. The gravitational force between different constituents of this cup is negligible compared to other forces which are essentially electromagnetic in origin. On the other hand, when you consider a very big object, then gravitational force become gradually more and more important. Like in the sun, the gravitational force is important to hold it together. And then if you take the object to be even bigger, then they become even more important. So this Jeans' stability is just determining what is that scale, what is the size at which gravitational forces become relevant. So what do we ask? We consider a big ball of matter with radius r and density rho and pressure P. So say this is a fluid, or this is a gas with some equation of a state. And so for instance, we have the Euler equation that governs the motion of the fluid elements. This is my so the co-moving derivative of velocity is equal to grad P minus rho times grad phi. So here, importantly, I'm including the gravitational effect. So we want this, we want this object to be, or let's imagine this is a stable, and these two terms have to balance each other. Or in other words, let us compare these two terms with each other. And here I'm just going to do a very rough estimate. So grad P the change in pressure is related to change in density via the sound speed. So grad P is of order CS squared times rho divided by R, where gradient are estimated at 1 over R. What about rho times grad phi? This is rho times Newton's constant times mass divided by R squared, and mass is rho times R cubed. So this is G rho squared times R. So now if I want the gravitational effect to become larger than the pressure effect, and that's the point when the object cannot resist the gravitational force and will collapse, then that tells me that R or R squared has to be larger than what I will call the Jeans scale, which is defined as CS squared divided by G times rho. So this is the regime of this is the regime of gravitational collapse. While R less than Rj is the regime which you can have pressure supported the structures like the sun. Now, if let's say now we are in a matter-dominated universe. So after Z of order 3000, the universe becomes matter-dominated. And in this matter domination, we have fluctuations with different wavelengths. We want to understand what happens to those. So if we are in matter-dominated universe, then G rho is of order of the Hubble square, right? This is just the Friedmann equation. So up to a factor of 8 pi, which now we are doing an estimate, so it doesn't matter for us. G rho is of order H squared. So what we see, and also for matter CS, is much less than 1. Right, so the sound speed for non-relativistic matter. So when we say matter, we really mean non-relativistic matter, right? And for that, the sound speed is much less than 1 because it's non-relativistic. That means that the Jeans length is much less than, well, it is CS divided by the Hubble scale, and therefore it is much less than the much less than the Hubble scale. So what it means is that there is a lot of modes, a lot of fluctuations which are sub-horizon. The co-moving wavelength is less than smaller than the co-moving horizon, but they are much bigger than the Jeans length. And those are all subject to this gravitational collapse. And this is basically what happens to them. They gravitationally collapse and form halos that become the host of the galaxies that we see. So this is the end. Questions?